So far in our discussions of covalent bondings, we've mainly focused on single bonds, when atoms share one pair of electrons, 2 electrons total. As I mentioned, atoms can actually share, non-metal atoms really, could actually share more than 2 electrons between them. So at this point, we want to talk about and introduce you to what are known as double and triple covalent bonds, which are usually just known as double and triple bonds. So a double bond occurs when atoms share 2 pairs of electrons, or 4 electrons total. And a lot of times the way you see a double bond, and I'll use carbon as the example here. Usually when you see a double bond between atoms, you see 2 lines between the atoms, where of course each line itself represents 2 electrons. So you'd have 2 electrons here, 2 electrons here. So these 4 electrons, remember, shared electrons count for both atoms that are sharing them. So these 4 electrons would not only count for this carbon, these 4 electrons would also count for that carbon. So when atoms share 2 pairs of electrons between them, 4 electrons total, you have what is known as a double bond. And then finally, you have what is known as a triple bond. A triple bond occurs when atoms share 3 pairs of electrons between each other, or 6 electrons total. Again, using carbon as an example, the way that you would see a triple bond between atoms is that you would see 3 lines between the atoms. And again, each line representing 2 electrons, so 2, 4, and 6. And therefore, these 6 electrons would count for this carbon on the left. These 6 electrons would count for the carbon on the right. So let's take a look at an example or two, one that has a double bond or double bonds, and one that has a triple bond as well. So let's look at carbon dioxide. So we know carbon has 4 valence electrons. Each oxygen has 6 valence electrons. And the way we know that for oxygen is that oxygen is in group 16 or 6A in the periodic table. And if you're in group 16 or 6A in the periodic table, you have 6 valence electrons associated with you. So again, the goal for everything here, the goal for each is to get up to 8. So let's start to set this up. I'm going to have the carbon in the middle, and then we're going to have an oxygen to the left and an oxygen to the right. Okay. So if we start with the oxygen on the left, in order for that oxygen to get up from 6 to 8 valence electrons, it says, okay, let me share one of my valence electrons with the carbon, and the carbon has a valence electron to respond in kind. So they'll share 2 electrons between them. But the oxygen also says, let me share a second of my valence electrons with the carbon. And the carbon has another free valence electron to share with it in kind. So since those 2 atoms are going to share 4 electrons between them, what type of bond forms between those 2 atoms? What you get is a double bond. And that works out really well for the oxygen, because now the oxygen has 2, 4, and then the lone pairs here and here come along with the oxygen as well, 6 and 8. So that oxygen is now happy because it has 8 valence electrons total. What about the oxygen on the right? Well, the oxygen on the right wants to do something similar. It wants to get from 6 to 8. So it takes its 1 valence electron and shares it with the carbon, and the carbon still has a free valence electron to respond with in kind, to form a bond between. And then the oxygen says, okay, let me take a second of my valence electrons and share that with the carbon. And the carbon has 1 more valence electron that it could use to share with that oxygen as well. So again, what type of bond is going to form between that carbon and the oxygen on the right? Because they're going to share 4 valence electrons total, the type of bond that's going to form between them is going to be a double bond. And for the oxygen on the right, that's perfectly great, because that oxygen now has 2, 4, 6, 8 valence electrons associated with it. Now, what about the carbon? Well, the carbon is happy as well, because the carbon now has 2, 4, 6, 8 valence electrons associated with it. So in this case, you have double bonds between the carbon and each of the oxygens. All right. Let's look at one more example. Here we'll look at a diatomic element, N2. So nitrogen has 5 valence electrons. So the goal for each nitrogen is to get up to that magic number of 8. All right. So let's see how that starts to set up. And actually, let me just draw it a little bit differently. So there's one nitrogen. Here's the other. Okay. So for each nitrogen to go from 5 valence electrons to 8 valence electrons, not only are they going to share 1 electron each with each other, 2 electrons total, not only are they going to share 2 electrons each with each other, 4 electrons total, but they are actually going to share 3 electrons between each other, or 3 electrons each, I should say, 6 electrons total. So if they're going to share 6 electrons total between them, what you're going to get between them is a triple bond. Each nitrogen shares 3 electrons, so they're sharing 6 electrons total. And again, each nitrogen is going to carry over a lone pair with it. And upon doing so, when everything is put together, each nitrogen is happy because the nitrogen on the left has 2, 4, 6, 8 valence electrons. The nitrogen on the right has 2, 4, 6, 8 valence electrons. Just a thing to note, and that's the fact that hydrogen and the halogens do not form double or triple bonds. Hydrogen can't. Why? Because for hydrogen, the highest energy level where you have electrons is the first. And what's the maximum number of electrons you can have in the first energy level? 2. Now the halogens can, but for reasons that we won't go into in this course, they don't. Okay, so hydrogen can't, so it doesn't. The halogens technically can, but for reasons we won't discuss, they don't. Okay, so basically hydrogen and the halogens do not form double or triple bonds. They are involved in single bonds only.